was supposed to be here at some point, but I'm gonna have to go tap on him. Where he is.
Yeah.
Jason, like the sound speaker. I think that he might just be sitting at his desk. So I'll quickly grab him.
Right now?
Maybe right after we start.
Okay. Cool.
Okay, so I think we're going to get started. So welcome back, everyone. So today we're going to have a guest lecture by Richard Liao, who's a PhD student here at Berkeley. So Richard works with Jan Stojka, Joseph Gonzalez, and Ken Goldberg, mostly at the intersection of distributed systems and machine learning. So today he's going to tell us about the work he's been doing in distributed RL. Thanks.
Hi. So I'll be talking actually a little bit more than simply the work on distributed reinforcement learning, but actually some like history and context about parallelism and using like multi-core or multi-node compute in reinforcement learning. And so here's some context. In this class so far, you've probably already seen two main computational patterns for reinforcement learning algorithms. The first one, which is on the left, is when the agent acts on a given environment from a given observation from the environment, and then receives from the environment another state and reward. And this is usually the nice like canonical way of like capturing the essence and basics of reinforcement learning. Now, the second computational pattern that you might see very often is when you split policy evaluation and policy optimization into two distinct steps. Now, this is commonly seen in policy gradient methods or methods such as TRPO, and is commonly implemented in many libraries and papers. So the difference between this like original version versus this batch optimization is actually motivated by a computational objective, which is specifically how do you better utilize our computational resources to accelerate reinforcement learning. And so this is the question that we'll be focusing on for the first half of this lecture. And so we'll trace this history of parallel and distributed reinforcement learning algorithms, starting with DQN from 2013 and arriving in 2019 with this algorithm called R2D3. And we'll also cover a couple of distributed reinforcement learning architectures that don't directly fit into this lineage that I have displayed on the screen. So each of these like nodes that you see in this lineage is a different paper, and each paper claims to be better than the previous. So, so I'll try to motivate some high-level trends and ideas for each algorithm, and then after talking about like the history of reinforcement learning algorithms for distributed computation, I'll talk about RLib, which is an open source project we've been working in the RISE lab. That provides high-quality implementations of these algorithms and components for people to use and also to scale the reinforcement learning algorithm separately. So, so let's start off with the most simple, like deep reinforcement learning algorithm, which is DQN. It's not distributed or parallelized, but it does introduce a lot of the key ideas that end up becoming scaled, end up like influencing other architectures. So. The main pseudocode here is that like we have a agent that evaluates the environment. This environment provides us the new state and the new action, like the new reward, and we take all this data, the current state, that current action that we take in, the new state and the reward from taking this action, and we pass this into the replay buffer. Now this buffer ends up shuffling the data around, and we sample it, and we take the sample that we get from the replay buffer, and we use it to update our Q network. Now, so after we update the Q network, occasionally we also have a separate network that we use for stability, and that's like the target network. Now, mainly here we want to pay attention to a couple interactions. So the first one is this process that evaluates the Q network and the environment. So basically, how do we get the next action, and how do, like, this process of taking the action on the environment and then receiving the reward. This process eventually becomes abstracted into one type of component that we use in reinforcement learning distributed architectures. The other one is this replay buffer, which helps randomize the data. This ends up becoming a separate component that we scale. And finally, we have this this way of updating the Q network and the target network. And this update mechanism is also separately compartmentalized and then scaled independently. So after we have this DQN, now in 2015, 2 years later, we see our first large-scale deep reinforcement learning architecture called Gorilla. So again, these components that I mentioned just now, these are taken, abstracted away, and scaled to be replicated and to run on multiple nodes. And so in this particular architecture, we see 4 main components. The first component is the replay buffer, which is called replay memory here. Then we also have this learner, which handles the updating of the Q networks. And it also pulls data from the replay memory. There's this actor that we see on the bottom left-hand side, which is delegated to task of environment simulation, and also holds a copy, maybe out of date, of this Q network that we use to calculate like the next actions. And then we have this parameter server, which essentially holds a copy of the Q network and allows the learner to repeatedly update it with very high throughput. So within the experiments, so you might see that this is like 4 different components, but within the experiments of the Gorilla paper, they actually combine this learner and this actor into one process, like what we call like the bundled mode. And so and then this is replicated many times. In fact, like they use 100 copies of these in separate processes. And there's one centralized replay buffer, so it's like one process, and the parameters are sharded like 30 times. And note that like this is done almost half a decade ago. So a lot of these things are kind of like they end up influencing later the things that we do currently, but they're sort of out of date. So for example, like you'll later see that like the actors and learners are actually separated, and that actually improves performance as compared to in this particular paper, like they were the way they did things, they had to like merge the two together. So one key thing to note here is that similar to DQN, the way they actually update the network is by having one actor. Each of these 100 actors, they'll sample once from the environment, and then they'll fetch from the replay, and then they'll calculate the gradient with the learner mechanisms, and then they'll update the parameter server. But note that because you're only calculating one, or you're only sampling once from the environment, the amount of data that you generate is actually quite slow. And so this ends up being very, very expensive, and you'll see that like later on when people start changing this, or kind of like relaxing this assumption that you have to like update the neural network so frequently, and then also like sampling from the environment very infrequently, you'll see that like the learning accelerates significantly. But back in 2015, this was a huge deal because simply by choosing the right abstractions, we can outperform DQN on the majority of things that we cared about, which is mainly just Atari games. And so the key takeaway here to set the stage for the rest of the work is that scaling reinforcement learning by choosing the right abstractions can provide significant boosts to performance. And but one thing to note here is that like in comparison to distributed deep learning, there's something fundamental about reinforcement learning, which is that like we have to generate our own data instead of having a data set that's already created. And so as a result, like this lack of stationarity in this data distribution requires both theoretical and architectural changes in order to scale the learning process. So we've talked about DQN and Gorilla. So now, so after Gorilla, Google folks were able to basically outperform this distributed architecture with just a couple system changes and algorithmic improvements on a single machine. And this is in comparison to previously where you had to have like 100 different processes plus like many different shards for each of the components. And this algorithm was a huge deal. So we'll be talking about A3C now. A3C is a paper that provides significant improvements over Gorilla, as we'll see on the next slide. And the nice thing here was that it runs on a single machine. The main difference for the main reason why like the single machine case is important is because this allows us to avoid the network communication overhead from communicating within different components. And this allows us to kind of like deprecate the replay buffer. So if we avoid using the replay buffer, we are able to use a on-policy training loss. So specifically, A3C steps away from the DQN algorithm and tries to use a policy gradient loss, which is calculated with the samples that you generate and without using some weird like some buffering where we create like a data set and we need to do some off-policy training. So the main algorithm of A3C is as follows. You have these 16, where some number of workers, and each worker has access to a global set of weights. And the global set of weights might be in shared memory, which allows us to calculate it and update it very frequently. And so each process will run asynchronously, and it will evaluate the environment a number of times. So in the paper, they use like 5 different steps. So they would calculate they would do sample from the policy, then they would take the action that they got from the policy, and they update the environment. And they would do this 5 times, and then after that, you have now like a trajectory of 5 states. Now, after we have this trajectory, we'll calculate the gradient with respect to this data, this data that we've generated, and we'll take this gradient, and we'll we'll update the global set of weights. So after we've sent the weights to the master, so like the shared neural network weights, then we'll try to like sync a copy back. So there will basically be 2 copies, one which is like the shared memory one, and one is the one that we have locally. And this avoids like data corruption or like changing the policy in the middle of like sampling. And one thing to note here is that like with different workers with different copies of the policy, we can also change the exploration. And so like in the paper, what they did was each of these 16 workers that they used had a different exploration policy and this allows us to generate a different data distribution for each worker, and then they show that like this is able to accelerate our learning process. So specifically what that means, relating this back to the previous architecture that we looked at, which is Gorilla, we were able to increase the rate of update, which is attributed to the avoiding of network communication by sending everything on one machine. And then also we took multiple steps between each update, and this allows us to calculate more experiences and generate more data for learning. And we've also, the second big change was that we deprecated the replay buffer. And this is important because we were able to not only move faster, but the reason why we could deprecate the replay buffer is because we used this the sampling technique where we have all these workers generating a diverse set of data, and we can avoid this we can basically reproduce this shuffling mechanism that the replay buffer used to take place in. And so I guess the third big thing here was that this is the first or this is a movement away from Q learning, which seemed to dominate in the past, actually like started to spur a large number of algorithms being used for like specifically policy gradient learning. And so in terms of performance, we can see that on the first two lines we have DQ and Gorilla, and the mean performance for A3C with this with the LSTM model is basically 3 times better than the previous the Gorilla results. And so let's fast forward a couple of years later, and now we have this we take all the learnings that we get from distributed deep learning, which has made a lot of progress simultaneously separately from reinforcement learning. And in 2018, we have this architecture called Impala, which kind of merges the learnings that we get from distributed deep learning with reinforcement learning. And so specifically here, similar to A3C, we don't have a replay buffer, but what we do have is the separation of actors and learners. And so what happens here is that we have all these actors that are running their own copies of their environment and own copies of their neural network, and they're generating a lot of data, and what they do is they just directly send all this data through the network to a large number of learner processes. So you might have like multiple of these learners, which maybe they're all running the same neural network and they're doing some like R-reduce or some like gradient descent mechanism that is parallelized across multiple machines. So this allows us to update very quickly and also generate data very quickly, because now we're not blocked by, like, the actors are acting separately from the learning process. So recall that previously in A3C, we would have data that's generated and we have to calculate the gradient, and we have to like update the weights from the master. And so you might spend like 50% of your time generating data and 50% of your time waiting for data to be, waiting for like the learning process to take place. But now here, because these are separated, we're able to actually move very quickly in terms of the learning process. So one big problem here is that you might have a case where the learning is happening too fast, or like the actors, because these things are kind of decoupled now, you might have like actors which are training on the neural network that's very out of date. And so this causes this notion of policy lag, where the actions that are generated by the actors are lagging behind, or basically correspond to the policy that is not representative of what's like the best policy right now, which is the policy that the learners are updating. And so in order to address this, this paper Impala introduces an important sampling algorithm called vtrace, and in the experiments they are able to show that with vtrace they are able to stabilize the learning process here. And I'm not going to go into the math here, but you can look at more details in the paper. Again, so this kind of like reinforces the idea that in reinforcement learning, one departure from the way we do things in reinforcement learning is because there's this environment or this data generation component of reinforcement learning, we have to make algorithmic changes coupled with system changes in order to accelerate the learning process. So this is Impala, and this was a paper that came out in 2018, and it's kind of like the state of the art of what people actually use in a lot of the DeepMind papers. So another architecture for scaling out is called Apex, and it also has a recurrent extension called R2D2. They're basically the same thing. One just has an LSTM. So this method is kind of not in the direct lineage of A3C and Impala, but actually takes a step back to Gorilla, and we see these this replay buffer mechanism come back. And so what happens here is, again, we have the actors which are separated from the learning process. And these actors are running asynchronously and generating data. These data points will enter the replay buffer, and the learner process will sample from the replay buffer. Now, what is actually happening is that like the replay and the learner are kind of like independently scalable, and we have also an actor, and in the experiments they run up to 256 actors. And so one thing here is that like the novelty about this particular architecture is that there's a way of sorting the data that's in the replay buffer using this notion called distributed prioritization. And so previous implementations of DQN, specifically prioritized DQN, would initialize the replay buffer inputs. So whenever the actors generate data to be fed into the replay buffer, as soon as they enter the replay buffer, they're assigned a priority. And so this priority mechanism allows you to find out allows the learner to sample and produce a particular data distribution that should be that facilitates better learning. However, the previous work would actually assign the maximum priority to any new replay buffer, any new input to the replay buffer. And so, if you have the maximum priority, then they're going to be sampled first. Now, the problem with this is that so after you have this like maximum priority, as soon as they're drawn out of the replay buffer for the learning process, the priorities would be updated. And this priority might be like significantly lower than the maximum priority. So then you basically shuffle the data only after the learning process takes place. And again, like because it's like a replay buffer, the data isn't necessarily deprecated. And in high throughput cases where you have like 256 actors and a lot of data being generated, if you only take the most recent data that was being fed into the replay and you assign it with the max priority, what ends up happening is you only sample like the most recent data. And this ends up being very myopic and actually like impacts the learning process. So in order to kind of facilitate a better learning process that isn't so myopic, what they did was they just like removed this like maximum priority construction, and instead they calculate the priority on the fly. So as soon as you generate data, you also use the same neural network on the actor process to initialize these priorities. This allows like the data to be sampled from the replay later on to avoid the recency bias. And this might be something just that they played up in the paper. But this is actually a really nice result because they were able to scale like the DQN learning process by a significant factor, and they compared back to A3C, and first of all, they were able to scale really well, using up to 360 actors, and you can see across the board, the Apex DQN algorithms this Apex mechanism is supposed to just outperform all the other state-of-the-art methods at the time by accelerating the training process. I think one thing that I forgot to mention is specifically in the light of this comparison back to A3C is that A3C doesn't really scale really well because as soon as you have more than like 16 actors or 32 actors, you have all these neural networks that kind of like get out of date. So you can imagine like if you have 360 actors, you have like if you have like you can imagine like if everyone is just updating the neural network sequentially, the 360th actor is going to be essentially like on average like 360 updates behind. And if that's the case, then like you can be sending some updates or generating data that is so out of place that like you actually can hurt learning. And so the nice thing about Impala and Apex is they're able to decouple this and independently scale the data generation process separately from the learning process with a nice couple changes, including like vtrace and this distributed experience replay mechanism. And as a result, like you're able to better utilize your compute resources. So basically the state of the art right now that people actually use is Apex and Impala. And there's another recent paper that extended this replay buffer Apex mechanism with the support for using demonstration data. So this allows the agent to bootstrap the learning process with an initialized set of expert demonstrations. So this algorithm is called R2D3, which is just one step above R2D2, which is like this recurrent Apex algorithm. So R2D3 has just one basic change here, which is this introduction of this demo replay. And when you have the learner process and this actor process, the learner is going to sample with some probability from the demo replay and with some probability from the agent replay. And maintaining a separate replay buffer for agent experiments and expert demonstration allows us to do like this weird sampling mechanism, and also they're able to change the prioritization of sampling and expert data throughout the learning process. I don't have any results for this, but this is mainly just a kind of this overview of what type of architectures are being used now. So that's it for kind of like this DeepMind line of work. There's also some other interesting distributed architectures that I want to talk quickly about. So there's an architecture from Sergey's group along with some Google collaborators, which is a distributed architecture that interfaces with the real world via robots. So QT-opt is a self-supervised vision-based reinforcement learning algorithm or framework for performing closed-loop real-world grasping. So what happens in the QT-opt architecture is you start off in the left-hand corner with a bunch of robots that are continuously generating experiences. These experiences, so like the data, action, and reward, is loaded into a data store, and this data store is then sampled into the replay buffer. This replay buffer has both online and offline data, and there's a separate computational process that calculates the right target, so the Q value target on each data point. And after this Q value target is calculated, both the target and the data are stored in a separate buffer called the train. It's basically queued up for the trainer, these trainer workers, this GPU trainer to be pulled. And once the GPU trainer like pulls this data from this buffer, then you'll calculate these like async gradient updates, update a parameter server, and this parameter server will then be used for the robot to update its weights. Now, I think the one interesting thing here is that there's this Bellman update job which calculates these Q values, and this Bellman update actually can be done asynchronously in a separate process, and so what's nice about this is they actually scale up to like 1,000 different cores, 1,000 different jobs, each of them independently asynchronously calculating this update on a bunch of CPU threads, and this was important for them to scale up. And I think one thing to note here is that this is again a separation from the previous like dichotomy or previous separation of the four components, where we have learner, replay, actor, and parameter server, because like we note that in here, in order to get this like architecture to work, we have to actually come up with a separate mechanism that can actually be independently scaled, which specifically is this Bellman update. And so we'll talk about this a bit more later about like why this is important, because in reinforcement learning we see that a lot of these small things that new algorithms do actually require like independent, or like require a lot of like parallelism that can't be really fit into modern day architectures. And so what ends up happening is you have to like come up with your own reinforcement learning, or come up with your own distributed system in order to like get things to work. Another interesting architecture here to talk about is the evolution strategies architecture. And this was kind of a big deal back 4 or 5 years ago, where OpenAI was able to accelerate a lot of the physical simulation, so Majoko tasks, by using like a lot of cores at the same time. So specifically, evolution strategies is a massively parallelizable optimization mechanism, and they they run thousands of workers. Each of them have their own copy of the environment, and each of them also have their own copy of the neural networks. And each neural network is slightly perturbed by some noise value, and they'll evaluate like one trajectory and get like the discounted reward for that trajectory. And at the end of each evaluation, each worker will bring all these results back together, and we have a new updated set of parameters that is the weighted average of the previous one, and the weight average is weighted by the performance of each worker. And so this is a gradient-free method, or it avoids the gradient calculation, but it is easily parallelizable and is able to scale almost linearly with respect to the number of cores being assigned to or allocated to this sort of like learning task. And so this, I think, isn't quite used that often in reinforcement learning papers, mainly because it doesn't really fit into like the policy gradient and Q-learning kind of like history of things. But it is, if you're trying to do a real world task, it is probably a thing to consider in terms of if you have like a lot of CPU machines to use. Finally, I want to talk quickly about another use of parallelism in reinforcement learning, which is actually for hyperparameter tuning. And so I'll quickly talk about a state-of-the-art method that's used in DeepMind called population-based training. And so right now there's kind of like two, or back in the day there was like two common paradigms for tuning hyperparameters, and one's for using sequential optimization, and the second one is using parallel search. So sequential optimization, which is shown in the top row, is when you have multiple training runs that are completed in sequence, and after each training run is done, a new set of hyperparameters is selected, and the model is retrained from scratch with the new hyperparameters. This is a long running process. It takes a long time, but it does use minimal compute resources. The second method is simply by running everything in parallel, and this might be a grid search or a random search, but we're not able to reuse, like, we're not easily able to like reuse the process, or like kind of like the progress made on a single one run that is running in parallel with like another. And so this is obviously, this requires a lot of compute resources, but is kind of like time efficient. And so what DeepMind came up with was a population-based training mechanism, which starts off like a parallel search, randomly sampling hyperparameters and stuff. And each training run will asynchronously evaluate its performance, and if the model is, which within each parallel thing, if one model is underperforming, like the population-based training will terminate the training, and then it will it will replace that resource with a better performing model and possibly perturb the hyperparameters of that better performing model. So this allows the hyperparameters to be optimized online, and the computational resources to be focused on hyperparameter that have the best chance at producing good results. So one thing here is that like you can think of this as a way of like searching over either searching over like a space of different schedules, or also like you can think of it as if your hyperparameter isn't really affected by the progress, like the time it has taken, then you can think of this as like an online learning way of tuning hyperparameters. And even though this seems kind of like unprincipled, this method is actually used across Google and DeepMind. Even on like they've recently released a blog post about using this at Waymo, and with this initial release of this method, the authors were able to actually improve the state of results for a lot of different methods simply by taking these paper methods and like running PBT on it. So we see a bunch of different neural network architectures here, including like transformers, feudal networks, A3C. Yeah, so this might be something to consider if you're actually interested in optimizing the final performance of your training process. So yeah, so that's kind of it for kind of like context for what people do for reinforcement learning and parallelism within the space. And are there any questions? Otherwise, I can move on to the next part of this talk. Okay, so now I want to talk quickly about RLib, which is a open source reinforcement learning distributed library that we actually published in ICML and is a very popular open source project now today. So to give some context for RLib, hardware today is rapidly improving in performance and cost. Which means that the CPUs and GPUs that we have are getting better and cheaper. And we see this impact on research with many recent successes. These are including like AlphaGo Zero or Impala. These are driven not only by algorithmic improvements, but by leveraging specialized hardware and distributed computation. But the thing is, this isn't simply like, not everyone has the engineering resources to use this hardware improvements. The field of deep learning has greatly benefited from the wealth of software frameworks such as TensorFlow and Keras that accelerate the development and training of models. In contrast, for reinforcement learning training, which involves not only the training of the model, but also execution of rollouts, the management of different models, or even like model-based subtasks, there's a relative lack of scalable software abstractions. So this is kind of unfortunate because we see a lot of complexity in like the computational structure of reinforcement learning algorithms, and it seems that more complexity is being added every day. So if you look at what systems are out there that are available for reinforcement learning today, there are as many implementations, specifically over like 10,000, but the real question is like how general these implementations are and whether they scale. And so if you look at kind of like the most scalable implementations of these algorithms, you'll find that a lot of them are implemented using many different systems, including multiprocessing, MPI, custom distributed systems, etc. So the bottom line here is that there's a huge variety of algorithms and distributed systems that are used for implementations and these repositories, but there's very little reuse of components across all of these 10,000 repositories. Now, the fact is that this is actually not too surprising because there are many challenges for reusing these distributed components, right? So the first big thing is that even for one simple reinforcement learning algorithm, there's a wide range of execution strategies and decisions to be made, and each one of these choices determines how the code is written and which abstractions are exposed, right? So you might have decisions that you have to make, such as whether or not you're going to support like the cluster or like a single node case, whether you're going to target the GPU, the CPU, etc. And the main problem here is that specialized systems that we have today only capture a subset of this design space. We're also fortunate to have many different deep learning frameworks, but each deep learning framework has a different programming or parallelism paradigm. So if you stick to TensorFlow, you might use distributed TensorFlow, or if you use PyTorch, you might use MPI, or you even use Horovod. And you'll find that the programming model for all these things are just quite different, and the reuse between implementation is quite challenging. So finally, there's just a wide variety of algorithms with different structures. So we've already taken a look at all these things in the previous part of this talk. And within this paper, we do analyze the several families of algorithms. And you can see that while there are many similarities between algorithms, there's also a lot of variety, especially for the more complicated things. And so what we're really after is abstractions for reinforcement learning. And good abstractions are good because they let us decompose these algorithms into reusable components. Some goals that you would want to achieve include being able to reuse code across deep learning frameworks, being able to scale your execution across for any different algorithm that you have, and also make it easy to compare and reproduce. So before abstracting and looking at like what abstractions that RLlib provides, let's take a step back and look at the structure of RL training today. So you'll have, again, like you have an agent that takes actions in the environment, gets the next observation, gets the reward, updates the policy, and takes more actions. You want your agent to improve, so within the agent, you might have like policy evaluation, which does like the acting, and then you have the policy improvement operator, which does the learning and improves the policies based on experiences. And it turns out within this loop, there's many ways of decomposing. So for example, you might have something like a DQN, which is asynchronous, where there are a bunch of different, as this is similar to the A3C, but with a DQN loss, where you have many different actor learners that are executing this loop in parallel, and then synchronizing weights through a centralized parameter server. And on the other hand, you might have Apex, which is scalable version, as we talked about previously, where the loop is broken up into two different pieces, where you have actors that are collecting experiences in parallel, and a learner that is just learning on high priority experiences. Now, yeah, so this is the replay and the things that we talked about previously about Apex. Now, these algorithms have very different performance characteristics, as you saw. Apex outperforms DQN by an order of magnitude. But really, there's a lot of similarity. The policy that they use is the same. The trajectory post-processor, where they calculate like the discounted reward, is the same. And specifically for asynchronous DQN, they even use the same Q-learning loss. But as we see on just like the slide before, there's a lot of structural differences, right? So async DQN has an asynchronous optimization loop. It has replicated workers, and it runs on a single machine. And here we read async DQN similarly to A3C. So Apex DQN has a centralized learner, has like these queues across components to facilitate like this asynchronous management, and has a large replay buffer and scales to multiple nodes. Now, if you leverage techniques such as population-based training, you might get even more structural differences, where we have nested parallel computation, and the decisions that we make are based on intermediate results. And this is just one family of algorithms. We found that there's no existing system today from big data or the high-performance computing world that can effectively meet all the varied demands of reinforcement learning workloads. So if you put on your system set, then you kind of ask yourself, what are the requirements for a new system? And the goal of a new system would be to capture a broad range of reinforcement learning workloads, maximizing performance and providing fundamentally reusable components. So the first requirement under this goal would be to support stateful computation, which means that you have like deep learning frameworks and physics simulators or replay buffers that hold state. The second, so one thing to note here is that this isn't actually supported in a lot of the big data frameworks today. So like Spark is like stateless. The second thing is to support asynchrony. So this is required for high throughput algorithms such as A3C, and this is a fundamental limitation of systems such as MPI, which don't support things like nested parallelism, where you have like parallel actors, and within each parallel actor you might have some parallel computations such as like a Bellman backup. And finally, the last requirement, again, as we mentioned before, is to enable reuse by enabling easily composable abstractions. So again, so at UC Berkeley, we've built a new system called Ray, which is built from the ground up to meet these requirements. So RLib is builds on top of Ray to provide higher level reinforcement learning abstractions. Ray implements a parallel hierarchical task model with stateful workers, and the main benefit of this task model is that it's flexible enough to capture a broad range of RL workloads instead of having to leverage like a different specialized or like custom-made distributed system. And so this hierarchical task model, in comparison to the previous set of things that people would come up with, is able to span across like all the different design decisions that you might make in a reinforcement learning algorithm. And the nice thing about this is the way this works is that you can create like a Python class in the cluster, which is a stateful worker. It's like you can like launch these like short running tasks on these workers, and you can do this with high performance. And so here's kind of the example. So you have this like top level worker process, which then launches a bunch of like sub workers. And because we can support this like hierarchy of parallelism, you can end up doing more parallels, more subtasks under these sub workers. And by having this kind of like hierarchical expression within your distributed system, you're able to support various like ad hoc ways of doing parallelism that previous frameworks were unable to use or unable to do. So one example of this is you have like some training process where, so you have like some agent that at the very top level says, I'm going to, oh, did my thing die? Oh. I'm going to run training with various different steps, and basically that's going to collect a bunch of experiences. Each experience worker is going to then do some rollouts in between, and you can also do some more specific things, such as like calculate gradient updates or like do distributed training across multiple workers. So to take a step back from this example, we have a unified system that is able to execute all different types of computation, and this is a key for enabling abstractions in reinforcement learning. And the main thing that this leads to is kind of like this idea of a policy optimizer, which is offered by RLib, and policy optimizers are responsible for executing distributed computation and required to improve a policy. These policy optimizers operate over policy graphs, which are another RLib abstraction, and this encapsulates like core numerical computations of your algorithm. And you've already seen one example, which is like the DQN graph. And so by decomposing into policy optimizers and policy graphs, which are the two key abstractions, you can like basically reproduce the result of 7 to 8 papers simply by mixing and matching different optimizers and policy graphs. So this is the goal of abstractions, which is to make composing new algorithms very, very easy. So RLib offers many state-of-the-art algorithms, including spanning across different subdomains, including high-throughput architectures and multi-agent architectures. And RLib is, again, a popular open source project, so multiple algorithms are actually community contributions. So to sum up, RLib is beyond just a collection of the algorithms. RLib abstractions allow you to easily implement and scale your own novel algorithms, and RLib offers APIs for interfacing with different types of data or different types of environments that you might want to target, including multi-agent routines or even external data. So the API is very, very simple. If you want to do simple training, here's like a code example that shows you training a PPO agent for 1,000 iterations. And the nice thing about this is that the distributed and GPU computation is handled underneath the hood. And this abstracts away the complexity that we might have in designing a reinforcement learning algorithm on a distributed system, because everything is encapsulated away by the RLib abstractions. And it integrates very well because with hyperparameter tuning, because Array is able to support hierarchical tasks. And if you try out RLib, you can see that it's integrated with a lot of standard frameworks that you might use for reinforcement learning, including VizKit and TensorBoard. So that's it for the RLib section of this talk. To summarize, RLib addresses challenges in providing scalable abstractions for reinforcement learning, and if you want to check out more, it's open source and available at rlib.io. That's it. Any questions?
All right, were there any questions? Okay, cool, so thanks, Richard. So we're gonna move on to the second talk. So our second speaker is Jason Peng. He's a PhD student at UC Berkeley. His advisors are Sergey Levin and Peter Abil. So Jason has mostly worked at the intersection of computer graphics and machine learning, primarily for using deep reinforcement learning methods to animate simulated characters.
Okay, yeah, hi, I'm Jason, and I'm going to talk about some of our work on applying reinforcement learning to physics-based character animation. And our goal here is that we want to develop simulated agents that can perform a pretty rich repertoire of skills. And part of the motivation for this work is that character animation remains a very manual and labor-intensive process. And so one of the goals of computer animation is that we want to develop procedural methods that can automatically synthesize motions for humans and other animals. And over the years, folks in animation have gotten pretty good at building controllers that can perform some pretty sophisticated tasks. But one of the drawbacks of some of these more traditional techniques is that they tend to require a large amount of domain knowledge in order to design task-specific control structures for a particular task. So for example, we might spend a lot of time building a very nice walking controller. But now if you want a character to jump, then we essentially have to go back to the drawing board. So on the other hand, reinforcement learning allows us to use very general control structures to solve a large variety of problems. But one of the drawbacks here is that learning-based methods, they tend to produce motions that appear fairly unnatural. And it'll be a bit of a hard sell to use something like this for things like movies or games. So one of the goals of our work is that we want to leverage these reinforcement learning methods to develop characters that can perform a large variety of skills, but while also producing behaviors that appear natural when compared to their real-world counterparts. So the goal of our system here is that given a simulated character and a reference motion that we want the character to imitate, as well as some tasks that we want the character to perform, our goal is to train a control policy that enables the character to perform that task while imitating the given reference motion. So here we have a policy that was trained to kick a randomly placed target while imitating a spin kick. And kind of what we found out through this work is that a relatively simple method actually ends up working surprisingly well. So I'm just going to go over the setup a little bit. So as is usually the case in RL, our goal is to learn a policy that maps a state to a distribution of actions. And for our tasks, we will be representing the state using features that describe the configuration of the character's body. And then the actions from the policy will specify target angles for PD controllers positioned at each joint. And these are then used to compute control forces that will be used to drive the motion of the character. Okay, so now to train the policy, the reward function that we'll be using consists of two components. The first component encourages the character to imitate a given reference motion. And it does this by trying to minimize the difference between the pose of the reference motion and the pose of the simulated character at every time step. And then the second component of the reward function encourages the character to satisfy certain task objectives, like hitting a target. And to train the policy, the algorithm that we'll be using is proximal policy optimization, which is a variant on policy gradient, which I think is covered in one of your previous lectures. And then there are some additional tricks that we need to get everything to work, but for the most part, they're all pretty simple and straightforward. But so let's take a look at some of the skills that we can learn. So here on the left, we have a simulated character. And on the right, we have a reference motion recorded from a human actor. And I think in this case, the policy does a pretty good job at reproducing the walking motion. And if we replace the walking motion with a running motion, we can train a policy to run. And to show that it's really the reference motion that allows us to learn these more natural behaviors, here's what happens when we train a policy to run with our reference motion. And so, again, we can get back some of the silly behaviors that we tend to see in RL. Okay, we can also get the character to do some more fancier things. So here's a cartwheel. We can get the character to do some backflips. Here's a front flip. And a roll. So for all of these skills, we are just providing the characters with a different reference motion. It's then able to learn a pretty diverse set of skills. Okay, we can get a character to dance. Here's a kip up. And a head spin. You can get the character to vault. And to do a little bit of breakdancing. Okay, so the thing to note here is that the character is not limited to just playing back the same motions over and over again. So in this case, we can perturb the simulated character, and it's able to kind of adjust its movements in order to kind of recover from these perturbations. Here's the character practicing some kicks. And all in all, we've been able to learn a pretty large variety of skills just by providing the policies with different reference motions. So a common learning framework is able to acquire a large variety of skills, ranging from locomotion to acrobatics, from martial arts to dancing. And we are able to do all of this by more or less just minimizing the tracking error. Okay, so if we have the mocap data, we can learn a pretty large variety of skills. But what do we do when we don't have mocap? Say we want to simulate a T-Rex. Well, it's a little bit difficult to mocap a T-Rex. But what we can do in these situations is that we can have some artists animate some keyframe animations. We can then use the keyframes as a reference motion and train a T-Rex to walk. We can also train a dragon. And even though the character's morphology is quite complex, the system still does a fairly good job at controlling this fairly high-dimensional system. Now, we can also train a lion to run. And now that we have a simulated model of a lion, we can then lay on top some high-fidelity muscle simulation and rendering to produce a pretty realistic-looking character. Okay, so far we've been looking at training policies to imitate individual reference motions. But we can also train a policies to perform some additional tasks. And here again is the policy that was trained to kick a randomly placed target while imitating a spin kick. And the thing to note here is that the reference motion just shows a single demonstration of a kick, but the policy learns how to adapt that one motion to kick a variety of different targets, and under some pretty heavy bombardment. We can also train a policy to throw a ball at a target by imitating a baseball pitch. And here's again is what happens if we train a policy without a reference motion. And again, we can get back some silly behaviors. And in this case, instead of throwing the ball at the target, the policy just learns to run towards the target instead, which is perfectly functional, but it might not look all that great. So another fun thing that we can do once we have a simulated model is that we can retarget motions from one character to another. So here we have a simulated Atlas robot imitating a spin kick from a human actor. And even though the character's morphology is quite different from that of the original actors, the policy still does a reasonable job at reproducing the original motion. We can also get the Atlas to run. If it falls down, it can get back up. And of course, it can also do some backflips. Okay, so if we have access to the mocap data, we can learn a pretty large variety of skills. But one of the limitations here is that mocap data can sometimes be fairly difficult to acquire. Publicly available data sets are still fairly limited, and recording new mocap clips often requires heavy instrumentation. So it would be nice if we can make use of a more accessible source of motion data. Well, video clips are an extremely abundant source of motion data, and YouTube alone receives over 300 hours of video uploaded every minute. So it would be nice if we can leverage this vast volume of video data to train our characters. And there's a lot of motivation for this work. Humans are able to learn a large variety of skills by watching other humans. And in the case of this baby here, he's able to learn all these moves just by watching TV. So can we get our characters to be like this baby? In that we want to be able to show our characters a video clip of some skill that we want to perform, and then have the character learn how to reproduce that skill on its own. So that's what we'll try to do, and here's the framework that we'll be using. Given an input video clip, we'll first process that video using a vision-based pose estimator, which will predict the pose of the actor in each frame. Given the set of pose predictions, we'll then reconstruct a kinematic reference motion that describes the motion of the actor in the video. And once we have the reference motion, we just apply the same reinforcement learning technique as before to train a policy for imitating that motion. So for the most part, we're just taking a fairly straightforward approach to video imitation. But let's see how well this works. And we'll start by looking at the pose estimation stage. So our goal here is, given a video clip, we want to predict the pose of the actor in each frame. And to do this, we are going to be leveraging some of the really great work that's been done in computer vision for pose estimation. And in particular, we'll be using a pose estimator called human mesh recovery, which trains a network to predict the pose of an actor from just a single monocular image. So once we have this pose estimator, we'll just apply to each of the video frames one at a time to predict the pose of the actor in each frame. And here's an example of some of the predictions that we get from this. So on the left, we have the original video clip, and on the right, we have the predictions from the pose estimator. And these vision techniques have improved drastically in recent years, and they can now do a pretty good job at recovering the pose, even just from a single monocular image. Okay, so that more or less takes care of the difficult part. Once we have the reference motion, we can then start training our policy. So here we have a comparison of the original video clip on the left, the reconstructed reference motion using the pose estimator in the middle. And then on the right, we have a simulated character that was trained to imitate the actor's motion. And in this case, I think it does a very decent job. We can also get the character to do some jumping jacks. And now if we want a character to do a backflip, we can just show a video clip, and it's able to figure out the rest. We can also imitate a front flip and a spin. We can also get a character to vault, so to roll. Here's the vault. And we can also imitate a kip up. I'm still kind of surprised that this one managed to work. But as before, we can also retarget motions to characters with different morphologies. So here's the simulated Atlas robot imitating a handspring from a video clip. You can also get the Atlas to jump, to vault, and to do a little dance. And one of the advantages of having these simulated models is that we can now start adapting the motions to different scenarios. So here we have a policy that was trained to do backflips across irregular terrain by imitating a video clip of a backflip on flat terrain. Here's a policy doing some cartwheels across some gaps. And I think for the most part, it's doing a pretty decent job. Oh, no, okay. It does still make some mistakes every now and then. But as a little disclaimer, this doesn't work all the time, and there's still plenty of video clips that we are not yet able to reproduce. So one failure case is that while the pose estimator does a pretty good job most of the time, it can still make some pretty big mistakes every now and then. And these errors can propagate to a simulation, and we end up with a result that's quite different from what we see in the original reference motion. And another failure case is that even when the pose estimator does a good job at recovering the reference motion, the learning algorithm may not be able to closely reproduce that particular skill. So one particular example is that video clips with fast dance steps still tends to be pretty difficult to imitate. But all in all, we've been able to learn a pretty large variety of skills just by imitating video clips. And for the most part, we're just taking a fairly straightforward approach to this problem. Okay, but one thing to note here is that all of the results I've shown so far, we've been training separate policies for each skill. So this means that every time that we want the character to learn a new skill, it essentially has to start from scratch again. And this is incredibly inefficient, and it's pretty undesirable, and it's pretty unsatisfying. Since it seems like if the character knows how to walk, that should provide it with a pretty strong prior on how we might go about learning how to run. So the motivation for this work is that we kind of want to leverage motion imitation as a way of learning a set of reusable and composable primitive skills that will then allow the character to tackle more tasks. And hopefully, these kind of primitive skills will also enable our agents to solve more challenging tasks later on. So, here's an example of kind of the pre-training phase. And here we have a humanoid character that's imitating different walking motions. And the main difference between kind of what you see here and the results from before is that instead of training one policy to imitate every single motion, we're training a single policy that's, to imitate a variety of different clips. And kind of the plots on the right here is a visualization of what the different primitive skills are doing at each point in time. So once we've learned kind of a set of primitive skills, we'll then transfer them to some new tasks. So here we have a policy that's trained to dribble a soccer ball from one location to a goal, to a target. We can also train a character to perform a carrying task, where the goal is to carry an object from one location to another. So one thing to note here is that while we are pre-training the primitives using using mocap data, no reference motions are used for any of these transfer tasks. But thanks to the primitives, the policies still learn to produce fairly natural-looking behaviors, even in the absence of reference motions. Okay, we can also train primitives for controlling a T-Rex. And with this, we can train the T-Rex to play soccer. Okay, so the character is pretty complex. The task is fairly long horizon, but kind of has a very long horizon. But thanks to these primitives, our policies are still able to solve these fairly challenging tasks. You can eventually get it. Okay, so just to wrap up a bit, for the most part, the story here is that fairly simple methods can sometimes work surprisingly well. And kind of the key to getting all this to work really lies in a lot of the design details. And in the case of motion imitation, we've been able to solve a pretty large variety of tasks just by minimizing tracking error. And this ends up working pretty well even for video imitation. But in the case of video imitation, I think there's still a lot of room for improvement, and I think we're just barely scratching the surface. But kind of my hope is that these video imitation techniques will eventually allow us to kind of leverage the vast volume of video data to train our agents to perform a large variety of skills. And the code for some of this imitation work is also available online, so if you're interested, feel free to check that out. Okay, and I just want to wrap up by thanking all of my collaborators who are really the ones who made all this work possible. And that's about it. So any questions? Yep.
Did you use some kind of smoothing for the motion? So like a lot of the pose was kind of erratic at some points in time.
Yeah. So one of the issues is that with the pose estimator, we are estimating the pose independently for each frame. So between adjacent frames, there might be kind of some large pose changes, and that can produce some artifacts. So we do have some post-processing to smooth everything out. Yep.
So there's no way to do this with like traditional control, right? So this is all like only RL is.
Yeah. So I think for some of the more traditional, let's say model-based methods, they tend to have a lot of issues with like contact-rich motion. So let's say rolling or crawling, and so there are some work that tries to apply some of these more traditional techniques to some of these more acrobatic motions, and there have been some successes there. But I think like if you want a very general system that can kind of learn all of these skills, then some of those more traditional methods might not be as scalable.
Can you comment on applications of this outside of animation, let's say especially in education, let's say in the younger years, K-8, or in performance sports?
Yeah, so I'm not too sure about like education for kids, but then I can see that there might be some applications of this for things like sports. So let's say if you want to have a stuntman or like an athlete, let's say perform some routine. And like, if you have a nice simulated model of a human, and you can train an agent to perform that routine, you might be able to kind of like draw some like strategies that might then be useful for, let's say, a real actor as well. That might be possible, but I think you probably need a much higher fidelity simulated model to kind of get any useful inferences from that. Yep.
Just comment on the kinematics or physics when you have an odd number of limbs, mainly the tail on all the other actors that you had there, the dog, the T-Rex, and the dragon. How was that handled?
So in the end, it's just articulated rigid body. So even an odd number of limbs doesn't really matter.
So there was no special processing teaching the T-Rex to play soccer with its tail wagging around?
Yeah, no. So for the most part, we are just applying the same system. It's fairly general. Kind of the caveat is that you need the right reference motions, which will be character specific. Okay, anything else? Okay, cool, thank you.